Good morning, friends. Already we discussed about the first numerical of exercise 13.1 to find out the atomic mass of lithium having the two stable isotope, right? And proportion of its isotope and mass of isotopes are given. We calculate the atomic mass of lithium. And also we find out the abundances of the isotope of boron in B part. The same numerical is 13.2. Here the three stable isotope of neon are given: neon 1020, 1021 and 1022. Here the respective abundances of 90.51%, 0.27% and 9.22%. The atomic masses of these isotopes are 19.99 atomic mass unit, 20.99 atomic mass unit and 21.99 atomic mass unit respectively. Obtain the average atomic mass of neon. The same equation, the atomic mass of the neon is equal to average mass of its isotopes. That means the sum of masses of the isotopes divided by the total abundances. For that purpose, we can write the equation like this way: the atomic mass of neon is equal to average mass of its isotopes. Therefore, the mass of neon is equal to, first, isotope neon 1020 as the percentage is 90.51, its mass is 19.99. Therefore, 90.51 multiplied with 19.99 plus the second isotope, and the proportion is 0.27 and its mass is 20.99 plus third isotope neon 1022, the proportion is 9.22 and its mass is 21.99 divided by total abundances 90.51 plus 0.27 plus 9.22. Right? So this way the total addition is 20.1771 atomic mass unit. That means 20.1771 atomic mass unit. Therefore 20.18 atomic mass unit, that is the mass of neon. That is mass of neon. Okay. Okay. The same as the earlier example 13.1. Only we have to apply the equation of atomic mass of the given substance is equal to average mass of its isotopes. Average mass of its isotope, that means the sum of the masses of the isotope divided by the total abundances. Okay? So this way we obtain the mass of the neon is equal to 20.18 atomic mass unit. Okay. After that, the next, obtain the binding energy in mega electron volt of nitrogen nucleus N714. The mass of the nitrogen is given 14.00307 atomic mass unit. Right? So how we calculate it? So first in nitrogen N714, 7 proton and 7 neutrons. 7 proton and 7 neutron are in nitrogen atom. Therefore, the mass defect, first we have to find out the mass defect. Delta M is equal to, our equation is number of proton Z mass of the one proton plus number of neutron into mass of the neutron minus mass of the nucleus. Here the mass of the nitrogen, you know, mass of the nitrogen. So the mass defect delta M is equal to Z. Number of proton are 7. Mass of the one proton is, already we know that the mass of the single proton is 1.007825 plus 7 neutron, and mass of one neutron is 1.008665. Right? That is the total mass of the proton and neutron in nitrogen nucleus minus mass of the nitrogen. Mass of the nitrogen is given 14.00307 atomic mass unit. Thus we obtain the simplification of this bracket is 14.11503. 14.11503 minus 14.00307. Therefore, the mass defect is 0.11236 atomic mass unit. That is the mass defect of nitrogen. Now, we have to find out the binding energy. Therefore, the binding energy of nitrogen is, that is the EV is equal to mass defect into binding energy of one atomic mass unit 931.5 MeV. Because we know that one atomic mass unit relation between the mass and energy is 931.5 MeV. We have the mass defect in atomic mass unit. So one atomic mass unit is equal to that much binding energy. So corresponding to that much mass, what is the binding energy? Therefore, multiplication of these two quantities, therefore 0.11236 into 931.5 is equal to 104.7 MeV. That is the binding energy of nitrogen. 104.7 MeV. Okay. Okay. To find out the binding energy of any atom or any nuclei, first we have to find out the mass defect of this atom. After finding the mass defect in atomic mass unit, we have the relation one atomic mass unit is equal to 931.5 MeV. Already we obtained this relation in illustration. So this mass defect is directly multiplied with 931.5. We obtain the binding energy in mega electron volt. Clear? Okay. So this type of the numerical are most important for objective and also in exercise numerical of 3 marks. Okay. The same question, 13.4 numerical. Obtain the binding energy in mega electron volt of the nuclei Fe 2656 and bismuth 83209. The mass of the Fe nuclei 55.934939 atomic mass unit, and mass of the bismuth nuclei 208.980388 atomic mass unit. Clear? Okay. Now, first we calculate for the Fe. In Fe, atomic number is 26 and 56. Therefore, 26 proton and 30 neutron in Fe. 26 proton and 30 neutrons are present in Fe nuclei. Therefore, the mass defect is mass defect of Fe delta M is equal to ZMP plus NME minus mass of Fe nuclei. Now, the number of proton in Fe is given as the 26. Therefore, 26 into mass of the one proton 1.007825 plus number of neutron is 30. Mass of the single neutron is 1.008665. Minus mass of the Fe nuclei. Fe nuclei has the mass is 55.93, 4939. As we simplify it, we obtain that is the 26.20345. 26.2345 plus 30 multiply this, so 30.239 minus mass of Fe 55.934939. Thus the mass defect is 0.5286461 atomic mass unit. And binding energy of Fe, Eb, is equal to mass defect delta M into 931.5 MeV. We know the relation, one atomic mass unit is equal to 931.5 MeV. Right? Now the mass defect is 0.528646. 528646 multiply with 931.5. Thus we obtain the binding energy of Fe is 492.26 MeV. Here we have to find out only the binding energy of Fe. But sometimes they will also ask, find the binding energy per nucleon of Fe. Therefore, binding energy per nucleon, that is the EBN, is equal to Eb upon atomic mass number A. Atomic mass number A. That means the 492.26 MeV upon 56. Upon 56. Therefore, 8.79 MeV. 8.79 MeV. That is the binding energy per nucleon for Fe. Similarly for the bismuth, right? In bismuth has the 18209. In bismuth, 83 proton and 126 neutron. Because the 209 minus 83, that means the 126 neutron. Therefore, mass defect delta M is equal to ZMP plus NMN minus mass of bismuth nuclei. Minus mass of bismuth nuclei. Substitute here the value of Z83. Mass of the proton is 1.007825 plus Number of neutron 126, mass of the neutron is 1.008665 minus mass of the bismuth nuclei 208.980388 atomic mass unit. Right? So do yourself. So thus you obtain the mass defect is 1.760877 atomic mass unit for bismuth. Do yourself. Therefore, binding energy of bismuth nuclei, that is the EB, is equal to delta M into 931.5 MeV. So the answer we obtain is 1640.3 MeV. And binding energy per nucleon EBN is equal to 1640.3 upon 209. That means the 7.85 MeV is the binding energy per nucleon for bismuth. Right? So here the same numerical 13.3 and 13.4. 13.3 we find out the binding energy for nitrogen. Now in 13.4, first we find out the binding energy of Fe and then the binding energy for bismuth. The same method, the first we have to find out, or we have to calculate the mass defect of Fe. Fe has the 2656, that means the 26 proton and 30 neutron. Therefore, using this equation, delta M is equal to ZMP plus NMN minus MFE. We can calculate the delta M is equal to 0.528646 atomic mass unit. We know that the 1 atomic mass unit is equal to 931.5 MeV energy. There is the relation between the mass and energy for 1 atomic mass unit. So directly we can calculate the binding energy for Fe. That is the 492.26 MeV. And binding energy per nucleon, this total binding energy divided by the number of nucleon for Fe, number of nucleon are 56, therefore 8.79 MeV. Now for bismuth, do yourself, only the sum step are written. For bismuth, 83209, 83 proton and 126 neutron. Equation of the mass defect, delta M is equal to ZMP plus NMN minus M of bismuth nuclei. So after substituting the value, we can calculate or we can obtain the mass defect of bismuth is 1.760877 atomic mass unit. Therefore, the binding energy of bismuth is delta M into 931.5 MeV. So we obtain 1640.3 MeV. And binding energy per nucleon, this binding energy is divided by the number of nucleon 209. So we obtain 7.85 MeV. Right? So this way we can calculate the binding energy and binding energy per nucleon for different atoms. થોડું નાનું કરું છે. Now, after the discussion of numerical of exercise 13.3 and 13.4, we calculate the binding energy of a given nucleus and also the binding energy per nucleon. Now, 13.5 is also the same numerical but quite different. Okay, now 13.5, a given coin has the mass of the 3 gram. Calculate the nuclear energy would be required to separate the neutron and protons from each other. For simplicity, assume that the coin is entirely made of the copper 2963 atoms. The mass of the copper nucleus is given 62.92960 atomic mass unit. So we have to calculate how much minimum energy is required to separate the proton and neutron from the 3 gram copper coin. For that purpose, first we have to find out the binding energy of copper by calculating the mass defect of copper, and this mass defect is multiplied with 931.5 MeV. After finding the binding energy for copper, we have to find out how many atoms are present in 3 gram copper coin. Right? And this binding energy of copper is multiplied with the number of atoms in 3 gram copper coin. So there is the energy required to separate the proton and neutron from the copper coin of 3 gram. Right? Therefore, first we calculate the mass defect of copper, then the binding energy, right? And then we calculate the number of atoms in 3 gram copper. Okay. For that purpose, first we take the copper 2963 in copper 2963, 29 proton and 63 minus 29, that means the 34 neutrons are present. Therefore, the mass defect delta M is equal to ZMP plus NMN minus mass of copper nuclei. Mass of copper nuclei. So, number of proton delta M is equal to number of proton 29. Now, the mass of the one proton is 1.007825 plus the number of neutron 34. Mass of the neutron is 1.008665 minus mass of copper atom 62.92960. So thus, as we multiply with 29 with this mass of the proton, we obtain 29.22 6925 plus multiplication of 34 with the mass of the neutron is 34.29461 minus mass of the copper nucleus 62.92960. Thus we obtain the mass defect directly. I can write 0.591935 atomic mass unit. Therefore, binding energy of copper that is the EB is equal to mass defect into 931.5 MeV. 931.5 MeV. Therefore, 551.3874 MeV is the binding energy of copper nucleus. Right? Okay. 551. Now, we don't separate the proton and neutron from the copper nuclei or the copper atom. We have to calculate the energy required to separate the proton and neutron from the 3 gram coin of copper. Therefore, first we have to find out now the number of atom or the nuclei, copper nuclei in 3 gram copper. Now, the copper has the atomic mass is 63. Therefore, in 63 gram copper, that means in 1 mole copper, there are the number of nuclei on the atoms is equal to Avogadro number. Therefore, in 3 gram copper coin, the number of atoms are. Now, in 63 gram copper, numbers of atoms is equal to in. Therefore, in 3 gram copper, numbers of atoms N is equal to 1. Therefore, N is equal to Na 6.023 into 10 is to 23 into 3 divided by 63. So as we simplify, so we obtain 0.2868 into 10 is to 23 atoms in 3 gram copper. In 3 gram copper. Now, energy required to separate proton and neutrons from 3 gram copper coin is E is equal to EB binding energy into number of atoms. Binding energy is 551.3874 multiply with 10.2868 into 10 is to 23. So we obtain 158.17 into 10 is to 23. That much MeV energy is required. Now convert into joule. Convert into joule. Therefore, 158 into 17 into 10 is to 23 into 1.6 into 10 is to minus 19. So we obtain 2.531 into 10 is to 12 joule. That much energy is required to separate the proton and neutron from 3 gram of copper coin. Right? Similar as earlier, numerical 13.3 and 13.4. But here difference is that not only we have to calculate the binding energy and binding energy per nucleus, we have to calculate the energy required to separate the proton and neutron from 3 grams of coin. So for that purpose, first we calculate the mass defect of copper. After the mass defect, we calculate the binding energy of copper. After the binding energy of copper, how many numbers of atoms in 3 gram copper coin? Now, the binding energy of copper multiplied with the number of atoms in 3 gram, that gives the energy required to separate the proton and neutron from 3 gram copper coin. Clear? Now, after that, the next numerical 13.6 is cancelled. Now, next is 13.7. A radioactive isotope has the half-life of T years, capital T years. How long will it take the activity to reduce to? First is 3.125% and second is 1% of its original value. Right? Okay, here we have to find out the time to reduce the activity from initial to 3.125% and initial to the 1% of its original value. So we know the equation of initial activity and activity at time t. So we know that initial activity R0 is equal to lambda n0, and at time t is R is equal to lambda n. Take the ratio of these two. R upon R0 is equal to n upon n0. R upon R0 is equal to lambda lambda. Cancel n upon n0. Here, the final is given the 3.125. 3.125% divided by 100. Therefore, 1 upon 32 is equal to 1 upon 2 is to 5. 1 upon 2 is to 5. But we know that n upon n0 is equal to 1 upon 2 is to n. There is a equation 1 and 2. From 1 and 2 equation, we know that the n is equal to 5. N is equal to 5. Now, already we use this equation, n is equal to total time upon tau half. Total time upon tau half. Therefore, total time t is equal to n times tau half. N times tau half. Therefore, time taken to reduce the activity to 3.125 is n into tau half. Therefore, n into tau capital T is equal to 5 into t years. So, in 5 times t years, the activity of a given isotope is reduced to 3.125%. Now, B part is again the R upon R0 is equal to n upon n0 is equal to 1% is equal to 1 by 100. Is 1 by 100. Now, from exponential loop, n is equal to n0 e is to minus lambda t. Therefore, n upon n0 is equal to e is to minus lambda t. But n upon n0 is given 1 upon 100 is equal to e is to minus lambda t. Therefore, 100 is equal to e is to plus lambda t. Taking the ln both sides, therefore I can add directly 2.303 log 100 is equal to lambda t. Is equal to lambda t. Now, 2.303 log 100, therefore 2.0000 is equal to lambda t. Right? Therefore, 4.606. There is a multiplication of this. 4.606 is equal to lambda is not given. 0.693 upon tau half into t. Tau half is given capital T. Therefore, 0.693 upon capital T into small t is equal to 4.606. Therefore, small t is equal to 4.606 t upon 0.693. Right? Therefore, 6.646 t. It means the 6.65 t years. So in that much time, the activity of a given sample is reduced to 1% of its original value. Right? On the basis of the exponential law of additive disintegration, we can calculate the n upon n0. And here also the n upon n0 is equal to 1 upon 2 is to n. We can calculate the time to reduce the activity to the 3.125% or 1% of its original value. Okay, so there is also important numerical possibility to ask in board exam.